For molar conductivity, we have a formula that lambda is equal to 1000 K upon C. So from this we can say that, or we got that lambda is inversely proportional to concentration. That is, as the concentration decreases, the lambda value goes on increasing. For example, suppose here I have two solutions. The first one is containing acetic acid, that is CS3COOH, while there is another solution which contains a strong electrolyte, that is NaCl. So we have two electrolytes. The first one is acetic acid and the second one is NaCl. Acetic acid is a weak electrolyte and NaCl is a stronger one. Now lambda value, when acetic acid is dissolved in water, being a weak electrolyte, it dissociates partially and produces CS3CO minus and H plus. And dissociate partially means, suppose if I am adding 100 molecules of acetic acid, then out of 100, hardly 10 molecules get dissociated and 90 remains undissociated. So if let's measure the concentration and the molar conductivity. So initially I added 1 mole of acetic acid in 1 liter solution, so the concentration is 1 molar, and it's a molar conductivity. On measuring a molar conductivity, I got a value 60. So as I said, only 10 molecule has been dissociated. That means a very less number of ions are present in a solution. So the conductivity is going to be a lower one. So I added a small amount of more water. When more water is added, that means the dilution is carried out or the concentration is reduced. So let the concentration has reduces to 0.1 molar. And as the concentration decreases, more number of ions are forming. Because on dilution, the more dissociation occurs, and more dissociation means more ions will form, and due to which the molar conductivity will increase. So lambda, as the concentration decreases, the lambda value, that is a molar conductivity, will increase, and from 60 it becomes 75. On further dilution, that means on further decreasing of concentration, the lambda value still increases. That means from 75 it becomes 82 or 83. Again, on further dilution, this value, that means as the concentration is decreasing, this value goes on increasing. On more dilution, the value again increases, becomes 95. More dilution, the value becomes 97. And the value is again 97 only. That means I can say that as the dilution is carried out, means as we are decreasing a concentration, the lambda value goes on increasing and increasing, as it is inversely proportional to the concentration, or simply I can say that on dilution the more number of ions are forming. For example, at 1 molar only 10, means when the concentration was 1 molar, only 10 molecule was in an ionic form, or they get dissociated into ions. On dilution, instead of 10, now 15 molecule has got dissociated. On further dilution, more number of molecules are getting dissociated and more ions are forming, and due to which the lambda value goes on increasing. But after certain dilution, as you can see that on dilution the lambda value increases, but that increase in the lambda value goes on decreasing. That is, that increase is a small increase, and ultimately after a particular number of dilution, you can see that lambda value becomes constant. After this, if you are diluting more, the value will remain 97 only. That means after doing a particular number of dilution, the lambda value becomes constant, and when the lambda value becomes constant, then it is called as molar conductivity at infinite dilution or zero concentration, and it is represented by lambda 0 or lambda infinity. Molar conductivity at infinite dilution, because we are getting this constant value after doing a large number of dilution, or it is also known as a zero concentration, because instead of calling like 0.000, we will say that the concentration is approximately 0. So this is called lambda value, that is molar conductivity at infinite dilution or at zero concentration. Means I can say this is the highest value for a molar conductivity for any particular solution. Now we have NaCl. Here I said that with the dissociation, like on the dilution, the more number of ions were forming. In case of NaCl is a strong electrolyte, and being a strong electrolyte, it dissociates completely and produces Na plus and Cl minus. Means if I have 100 molecules of NaCl, then in water all 100 molecules get converted into ions. Here also I measure the lambda value and on a particular concentration. So concentration is suppose initially 1 molar, lambda value I measure it was 80. When I am diluting, on further dilute means on addition of water, on the addition of water I will simply say, I can say that since all the molecule has been already dissociated, so the lambda value will not change on the dilution. But surprisingly, when we add means on the dilution, means after adding more water, even all 100 molecules has been dissociated into ions. But still after the dilution, that means after adding a water, this lambda value get increased and it becomes 85. On further dilution, the value is again increasing and it becomes 88. Now the question arises that here the molecules are already dissociated, means all the NaCl molecule has got converted into Na plus and Cl minus ions. Then why the value increases on dilution? Then simply I can say that when NaCl get dissociated into ions, then Na plus and Cl minus has been separated, but there is some weak force of attraction present between them. And when they conduct electricity, during the conduction they always moves in opposite direction, because there are the electrodes, positive and negative electrodes. So the positive Cl minus will move to this, Na plus will move to this. And when they migrate in opposite direction during conducting electricity, so that due to that weak attraction, what happens, the conductivity of Na plus is affected or it is stopped by the Cl minus ion, and the same way the Cl minus conductivity is affected by the Na plus ion. So what happens when I added water? Due to the addition of water, the volume will increase, and volume will increase, that means I can say the gap between the Na plus and Cl minus ion will increase, and due to this the attraction will become still weaker. On further dilution, they will again move away from each other, that means the attraction again decreases. So here after 2-3 times of dilution, the attraction slowly goes on decreasing, and after this 88 it becomes 89, and then on further dilution the value is 89 only. So here I can say that here of means in case of NaCl also on dilution the value lambda value goes on increasing, and here the reason for that increase in the lambda value is not the dissociation, like more dissociation is occurring, but it is the lambda value increases because that weak force of attraction between the ions get weaker and weaker, and due to which they moves faster, that means the conductivity increases. Now in case of weak electrolyte like acetic acid, to get that lambda value here the large number of dilutions are required. That means you can see that dilution has been done up to a concentration of 0.000, that is approximately 10 to minus 6 molar. While in case of strong electrolyte, after doing a certain number of dilutions, we get lambda naught value. This is the lambda naught value, that is molar conductivity at infinite dilution or zero concentration. So here compared to the weak electrolyte, the less dilutions are required to get that lambda zero value. Well, in this case more number of dilutions are needed. The reason for it, then simply I can say that here on dilution two things are happening. The first one, during the dilution, the first dissociation takes place, as well as in addition to dissociation, that weakening of the attraction between ions also takes place. While in this case during a dilution the dissociation has already done, means in the beginning only, that is there is all the 100% dissociation has occurred. So here during the dilution the water is only weakening that force of attraction, and that's why the less number of dilutions are needed for to get that lambda naught value, that is a molar conductivity at zero concentration. Now we have a relationship also between the lambda and lambda naught. Now suppose, see, I can say that here getting that lambda naught value, it's like a concentration 1 to 0.001 or 1 to this 0.0001 molar. That dilution appears like only 4 or 5 times, but that dilution requires a very large number, means it requires a very large number of dilution to get lambda naught. So we have two methods of getting a lambda naught. Either you keeps on diluting and you check that when the lambda value will become constant, or secondly we use a graphical method to get that molar conductivity at infinite dilution. So let's see how it is calculated from the graph. We have de Broglie-Onsager equation, and according to this equation we have a formula that is lambda is equal to lambda naught minus A square root of C, where lambda is a molar conductivity, lambda naught is a molar conductivity at zero concentration or infinite dilution. I can say A is a constant and C is a concentration. I know that the lambda value changes as the concentration changes, that is there is a variation between the lambda and concentration. Now let us comparing it. Y is equal to mx plus C. So I can say that if I am plotting this on y axis and root C on the x axis, then this lambda naught is going to be C value, that means it is going to be a y intercept, and A is going to be a slope, A is going to be a slope. And since the slope is a negative, that means the graph is moving from top to bottom. So when a graph is plotted, the graph of lambda versus concentration. As I said, there being a negative slope, the graph, suppose when the concentration is high, this is the concentration value, then another concentration term, that is a concentration is reduced, so the lambda value will increase. Then again the concentration reduced, that means on dilution the lambda value will increase. So after getting 3-4 point, that means we are just decreasing the concentration, and so that the lambda value also changes. So after getting a 3-4 point, we just use a extra plotting method, where after joining these 4 points, the graph is extra plotted. I know that the graph is always going to be a straight line, so the graph is extra plotted, and on extra plotting the graph will cut somewhere to the y-axis, and the point where it cut to the y-axis, that is a y-intercept, is nothing but the C value, that is a lambda naught. So the point where the graph cut or this y-axis is nothing but the lambda naught, that is a lambda value or molar conductivity when the concentration is approximately 0. So to get that lambda value, generally we use molar conductivity at infinite dilution or zero concentration, we generally use this method. But this method is applicable only when the electrolyte is a strong electrolyte. If the electrolyte is a strong electrolyte, then to get that molar conductivity at zero concentration, we can use this Onsager equation, or I can use this graphical representation or graphical method. But if it is a weak electrolyte, then weak electrolyte creates a problem, because in case of weak electrolyte, we never get a straight line. Instead of it, we get a curve. For example, suppose the concentration is high. When we start diluting, if it is a weak electrolyte, that is on reducing a concentration, instead of getting a straight line graph, we get a curve, and the graph is something like this then. And since we are getting a curve, so we cannot predict where it is going to, where it will cut to the y-axis, and that's why this method, that is a graphical method, is not applicable when the electrolyte is a weaker one. So it is applicable only when it is a strong electrolyte, not for the weak electrolyte.